All right. Oh, I'm going to have to call you back, Sherry. I'm sorry. Okay. All right, everybody. Let's get started on our last class before Thanksgiving break. And as a reminder, no lab. Because you all are working on your topo. Which, by the way, how's that going? Going good. For those of you that are remote connecting to the topo or for the computers in the room, one of the things that we discovered that you might need to check and make sure those computers are on. So we had one student who kept trying to remote connect to the computers, and we checked, oh wait, it's off. So that helped. So go to the computer lab. If you're planning on remote connecting into the computers in 2241, check and make sure it's on before you leave campus. So, okay, that topo is due Friday at 1, okay? It's due Friday at 1. Any questions on that? Everybody good on that? Any broad issues? One thing I'll mention, I did make a post on Microsoft Teams for a thread in case anybody had any global questions that I would respond there. There was one that if you're closing and reopening and you're not able to save your point query for the topo, that right-click that little pencil and then close and open for edit, and that'll fix it. Permission-only issues on your point file might be an issue there. But if there's any other big issues, let me know. Okay, sound good? Okay, I'm going to update the attendance grades at the end of the week. We're still grading homework 8, but the solution is posted. Lab 12 is being graded, and I'll tell you what's going to happen with Lab 12 is one of two things is going to happen. You're either going to get 100 on Lab 12, or if there's any deductions, probably for the sketch, like there were still a few north arrows missing and things like that. But other than that, like the calcs were all right, and the curve that you staked out was all right. So I think the grades on that lab are going to be very, very positive. I did want to mention the course eval. That's the survey where you all get to say how horrible a professor I have been all semester. I'm joking. But in all seriousness, it has been a very long time since I've taught geomatics, and I'm always eager to see what I can do to improve my classes. So I do really appreciate what you say. So, I mean, I do want you to do it. I am going to open a small bonus homework for doing the survey. You can say whatever you want about me. You can say I'm the worst professor ever, but I do want you to do the survey. And if you upload proof that you've done it, I don't want to see what you wrote. I just want to see that you did it. But if you upload proof that you did it, I'll add a small 10 points to your overall homework average. So it sort of translates to about a point in the class. So, but again, you can say I'm horrible, but I, in all seriousness, I am interested in what you say because I do want to improve. The only other thing I'll mention on the slide is this term, the at-home game, and you're probably like, what is the at-home game? How many of you who've had me for class before know what I'm talking about with the at-home game? Some of you know what I'm talking about. So the at-home game, I had a buddy in grad school, and what he would do is he would take his grades, and then he would figure out what he needed to get on the exam in order to get an A or a B or a C. He called that playing the at-home game. So I developed an at-home game spreadsheet. So the idea is what you can do is in these 5 orange cells, what you can do is say, here's my overall attendance grade. So let's say my attendance grade is a 90. Let's say I got about an 80 on the homework average. Let's say my lab average is pretty good. I had a rough day on the first exam, but the second exam worked pretty well. So my class grade right now is an 84.47, and then this will tell you what you need to get on the final in order to get an A or a B or a C or a D or what have you. So one thing I will tell everybody, because people ask, well, what if I get a 79.6? Will I round that up to a B? Yes, I round. I round to the nearest percentage point. Okay? Sound good? Is that fair? So I'll send that out a little bit later today. But the data that's in the cells when I send it out, these are just dummy values. Don't take them, bank. They're just made up values. But you can go in and enter the values and see where you're at. Okay. Any questions on logistics before we get on to earthwork land? Okay, let's talk about some earthwork. Today's focus is going to be primarily on volumes, but I don't want to rush the computation of the areas. And we sort of started to run out of time a little bit last time when we were looking at our cut section. So let me recap where we left off last time. And we had talked about, so we've already seen all this, so let me go back to our example. Okay, so let's go to here. Okay, so this is the example that we were looking at last time, and what we were doing is we were taking survey data collected. This would probably be from an actual differential level or an auto level. That's not to say you couldn't do it with the total station, but you could probably just do this with an auto level and just do some backsides and foresights. And so what we have is at a particular station along a roadway project, we have the height of the instrument. Then we have a series of foresights, so we can take the height of the instrument minus the foresights to get the elevations. So we have the elevations along the land, and then we have the distance from the center line. So this shot was taken on the center line, this is taken to the right, this is taken to the left. And the idea is, okay, how much cut do we need to generate? What is the area of the section? If the road needs to be at 858.9 feet and we want to use a 1 to 5 or 1.5 to 1 slope banked off that off a roadway template that's 30 foot wide, what's the area? Okay, so what I did last time is the first thing I did is I plotted out the survey data. So this is what the land looks like along that cross section, and then this is where the road is, right? Everybody with me on that? Okay, then so I've got A, B, C, D, E, and F, and then I'm doing G and H. So I'm going this way. So A, B, C, D, E, F, and then G, H, because I'm doing it clockwise. And I also stuck a point here in the middle, because I'll use that as a reference for later. Okay, now the next thing that I need to do is I need to say, okay, my excavation is going to be at a 1.5 to 1 slope. So I need to figure out where these intersect. And this is what we did last time. We figured out where that point was. We computed the coordinates of point R, and we got this when we did it by hand. So I did this one. I'm not going to repeat the next one because it's literally the same calculation. So if you can do R, you can do L. Was everybody okay with that? Everybody good with that? Okay. All right. So that's sort of like where we stopped, and so I don't want to rush this, okay? Now, if you recall, I mentioned that there were 3 methods that we're really going to focus on doing this by hand. The first is the computation of area using simple shapes. The second is the shoelace method, and then the third is using a template. Okay, so I've got the answers to all of these in the slideshow, and so you all have the answers to these. But I don't want to just give you the answer and just say just figure it out. I kind of want you to at least have a little bit of an understanding of where these came from. So I want to talk about the simple shapes computation. So what I'm doing here for this area computation is I'm taking this area. So what I want to do is I want to figure out the total amount of cut, the total amount of material that I'm removing from here. So what I'm doing is I'm splitting this up into a series of simple shapes. Okay, and so I've got 1, 2, 3, 4, 5, 6 of them. Okay, and the way that I'm doing that is I've got a little bit of a blown up version here on the board. So all I'm doing is I'm finding these like unique points and just drawing vertical lines. Okay. So what I've got here on the board is just sort of a zoomed in version of this region right here. So let's take a look at what we've got going on here. Okay. So I've got the coordinates of point B, point C, and point D plotted here, as well as the coordinates of O and H. Okay. I'm actually not really going to use O over here. I just sort of have it there for reference. Okay. So what I'm going to try and do is I'm going to try and figure out the area of these 2 shapes. Now, this is a triangle and this is a trapezoid. Now the area of a triangle is pretty easy, right? We're just going to take base times height over 2, okay? So this is the base, this is the height. And as for the trapezoid, what I'm going to do is I'm going to take the base, and instead of taking like base times height over 2, what I'm going to do is I'm going to take the base times the average of these 2 heights, right? So the average of this one times the average of this and this will give me a height multiplied by the base will give me the area. So the area of this first shape is just BH over 2. The area of the second shape is the base times the average height, right? So what I need to do is ultimately I need to figure out what these dimensions are, okay? Now, the first thing I'm going to figure out is what are these base values. And these are actually really, really easy to figure out. Okay? So let me kind of give you a point of what I'm talking about here. Okay? So what I'm going to try and do is I'm going to try and figure out the coordinates of these new points. So I've got point B, point C, point D, point A, what have you. I've got this point C, and see how I've struck a vertical line and it's sort of hitting this spot right here? So I'm going to call this C prime, okay, because it's right under here, okay? And I want to try and find the coordinates of this point, okay? Well, I propose that I already know what the x coordinate is. The x coordinate is 20, or negative 20, because if the x coordinate of this is 20, I'm going down, that's the same coordinate right here, okay? What I need to figure out is what is the y coordinate, right? And I propose the y coordinate is going to be somewhere between this and this, right? Because it's on this diagonal line, I just need to figure out what that is. Does that make sense? Everybody okay with that? And so similarly, I'm going to try and find this, which I'm calling h prime, or sorry, h prime. Let me move this over here. So that's going to be, you know, some coordinate. What's the x coordinate of h prime? What is this value right here? Negative 15, right? And how do I get that? Because it's just a straight line up for this, right? So I need to figure out what that is. Okay, with me so far? All right, now, so my main goal is to try and figure out these coordinates. So once I figure that out, the rest is pretty straightforward. But I do want to mention that there's some values I could probably figure out right now, and that's B1 and B2, okay? Let's start off with B2, okay? What is the x coordinate of this line right here?
Negative 20.
What's the x coordinate of this line right here?
Negative 15.
So how wide is that?
5.
5, exactly right. Right, so I've got 5 right here. What about right here? What is the x coordinate right here?
Negative 33.8.
There you go, and the x coordinate right here?
Negative 20.
So this is
13.8.
13.8. So if you see here in the slide, see how I've got, oh, I labeled it backwards. I did h's and b's. It doesn't really matter. But see how I've got this 13.8 and 5, right? So now what I'm going to do is I can see if I can fill in the rest of this right here. So let me show you how you would do that. It's pretty straightforward, okay? Let me break out the notebook here. So we'll get to the volume computations here in a bit. So this was the problem that we did last time in class. This is what you all have in your notebook. So this is when we were trying to figure out the coordinates of R, okay? And so what I'm going to do is I'm going to continue on with these calculations, and I'm going to say, here's how you would figure out, you know, some simple shape areas. So we'll sort of like do this, and we'll say, okay, here's what I'll do. I'll call this sample computations for simple shapes. And the cool thing about this is that if you understand these components, so remember there's 3 ways of computing these areas. There's simple shapes, there's the shoelace formula, and then there's the template, the section templates. If you understand these computations, then the section template computations are going to be very easy because it's using a lot of the same math. Okay, so let me show you how we would do this. And so I'm going to sort of piggyback on what I got going on right here. Okay, so here's how I'm going to do this. All right, so let's start off with this first area. We'll call it A1. So I'm going to try and figure out, bless you, I'm going to try and figure out the area of this triangle. So it's going to be BH over 2. So I need to figure out H1. And so my goal is to try and figure out the equation of this line LH. Okay, that's what I'm going to try and figure out. Now, L is negative 33.8, comma 871.4, and H is negative 15, comma 858.9. Okay, so I've got to believe that you all could figure out if I gave you a point and I gave you a point, that you should be able to figure out the equation of the line. We don't need to go through that in here. By the way, let's see if we remember what is the slope of this line? Remember, we were actually given that, right? This is 1 and this is 1.5, right? So the slope is 2/3, right? Or negative 2/3, I guess I should say, because it's going downwards, right? Change in y over change in x, right? So I propose that you all can probably do that pretty easily. And when you do that, you're going to get y equals negative 2/3 x plus 848.9. Okay? And so what I'm going to do is, and that's after figuring out, again, I'm sure you all can do that. So now what I'm going to do is I'm going to take in this expression, and I'm going to plug in my x equals negative 20 because I want to figure out what this value is right here. So I'm going to evaluate I can do better than that. At x equals negative 20. So y equals negative 2/3 times negative 20 plus 848.9. And when you chug that out, you're going to get 862.2. So therefore, the coordinates of C prime are going to be negative 20, comma 862.2. So that's going to be the coordinate of this value right here. So where this is negative 20, I can replace this part right here with 862.2. And let's just take a look at this. Does that make sense? I mean, this is 858.9. This is 871.4. Along that line, that's in the middle, or that's in between that. Does that value make sense? Okay. So let me ask you this. If I now know this coordinate, how do I determine H1? I'm asking you, how do I do it?
Subtract the y value of c.
And C prime, right? That's exactly right. So take those C prime, take the difference. So therefore, $874.7, right? Mm-hmm. Minus 862.2, and that equals 12.5, right? And so now that I have 12.5 and I've got 13.8, I just do base times height over 2. Does that make sense? Everybody okay with that? And so I can do the same thing for A2. Here, let me erase this. I can do the same thing for A2. Now that I've got this height, I can do the same thing over here. Find the equation of line CD, plug in x equals negative 15, get a coordinate, and then just keep on repeating. Okay, does that make sense? All right, so you tell me, do you want me to go ahead and do H prime, or do you all think you're good? You tell me. What's that? Y'all good? Okay, because I think at this point it would start to become somewhat repetitive, right? So what you would do is you would just keep doing that for every shape. And here's what you would get. And you would get an area of about 709.7. So here's this. So the first shape we have 13.8, 12.5. And so you can see where that came from. There's the 5. So we're going to have 12.5 on H1. And then you can keep on going until you get all the areas. This is a very Excel-friendly computation. Okay. So that's how you would compute the area with simple shapes. Honestly, I think the easiest way to do it is to use the shoelace formula, right? Because remember the shoelace formula, what we do is we start, so I started at point 0, I list all the coordinates of the area in question in clockwise fashion, so O, H, L, C, D, E, R, G, O, and then I list O again, right? And then I do all the products this way, then all the products this way, sum that, take the absolute value of the difference, divide it by 2, and bam. Now, if you're tracking your decimals, okay, you should literally get the exact same answer for the shoelace formula than you do for this, because these are both exact computations, okay? That makes sense? They're literally you're literally computing the area exactly. Where you should get a different answer is if you're using the section template. So the nice thing about the section template is that it's easy. It is very easy. because all you need, so the way a section template works is we just take a few base values, so a distance to the left, a distance to the right, a height to the left, a height to the right, and then a roadway width and a center height, and just plug and chug into this formula. So this formula is greatly simplifying what's going on from a geometrical standpoint. With that simplicity, you get an easy formula to compute, but you will not get the same answer. If you look at the real land is going all over the place. It's not fitting this nice, pretty picture that you see over here. So when you plug and chug into your section template expression, you're going to get a different answer than what you got if you do it for real, okay? But again, with ease, you sacrifice a little bit of accuracy. What I was saying earlier is that in order to use a section template, you need these FL and FR heights, but you can get that doing this, right? So once you get those, you can use those values for both a simple shape computation and for your section templates. Does that make sense? All right, any questions on that? All right, so when it's all said and done, here's the results of the example. And again, these two will give you the exact same answer. This one will be a little bit different. And I say exact because dependent upon how you do this, if you're tracking rounding or you're rounding things differently, you may get a slightly different answer, but they should be like theoretically the same. All right, any questions on the area computations? Everybody good? Let's talk about volumes. Okay. All right. Let's get into volume computations. Okay. All right. So, again, let's just get back to big picture, okay? And to be clear, some of this discussion that we're having today will probably trail a little bit into after break, because we probably won't get to mass Hall diagrams or to compaction and things like that, but we'll at least cover the basics of some volume computations today. So remember, if we're talking about a root-based project, we've been looking at it in 3 different contexts. So we've been looking at the plan view, bless you. We've been looking at the plan view, and so in the plan view, we were considering the installation of horizontal curves to create a smooth track. Vertical curves along the profile view will also add for a smooth path. But right now we're talking about earthwork calculations. And our goal is to really calculate volumes, okay? Now, remember, when we're talking about earthwork, when we're talking about construction, we're talking about moving soil, removing earth or rock from one place to the other, and so we have terms for that. Cut is when we take a material that is removed from its natural location, and fill is when we place it, and more specifically compact it in a different location. And so we ultimately would like to balance the cut and fills. Like if we added up all our cuts, added up all our fills, we would theoretically like those to be 0, okay? And the way that we compute volumes, theoretically, is we sort of take areas times lengths. Now, I'm going to get more specific with that today, and you'll see what I mean. That's generally kind of the idea. So you do kind of need areas first. So in the previous lecture, I was hyper-fixated on how to compute those areas. Today, I'm going to assume, let's say you have those areas, now let's do something with them, okay? So let's talk about some volume computations. I'm skipping this because we just talked about all the different ways we can compute areas. Okay, so let's go back. So we had this image in our slides last time. This was a roadway alignment, and we're talking about it in 3 dimensions, okay? And I want to focus on this in a little bit more detail. So last time, if you remember, let's take this project. We're starting at station 10 and going all the way up to station 13. Now from station 10 all the way to station, I think we have 11 plus 21, these are all fill stations, right? So we've got to raise the surface of the existing ground to meet the target of the road. Everything from station 1164 on is all cut, so we're removing material here. So this material that we're removing will probably come down here. And from here to here, we've got a little bit of a transition. Some cut and some fill. Everybody okay with that? Okay. So I want to sort of show you what cut and fill computations look like. And so what we're going to have at each station is we're going to have a series of areas. Okay. So for example, at station 10, we have an area, and notice how there's an area just for a fill. Whereas at station 13, there's an area, and it's an area only for a cut. Now that should make sense because we're filling here, and we're cutting here, bless you, okay? So we got a really big area right here, maybe a not so big area, I don't know, right here, okay? But notice how in the middle, we've kind of got both, right? 1121, 1140, 1164, we've got both cut and fill areas. But this is where it's transitioning from a cut to a fill along the route of the project. Make sense? So this would be a situation where we have, I don't know, an existing ground that looks like this, and we want the road to, look like that. So this is going to be a cut, and this is going to be a fill. So that station, for example, is going to have both a cut area and a fill area. Make sense? That's a transition. Everybody with me so far? Okay. So I've got a couple, so here's my computations, and I'm just sort of throwing them at you, but I really want to focus on these three questions. Okay, so the first question is, how do we compute these volumes? Like, how do we compute the volume right here, the volume right here, the volume here? Like, how do we actually compute those? So we're going to talk about that today. The second is, how do we handle the unit differences? Did anybody notice that? Did anybody notice that these areas are in square feet, but these volumes are in cubic yards? Anybody notice that? And when we're typically discussing earthwork volumes, earthwork, we're talking about moving earth across an entire road. We talk about that in cubic yards, not usually in cubic feet. So we've got a units issue we got to address. But then here's another one. What is up with this 25%? Why is Dr. Mike just magically taking the fill volume and just increasing it by 25% just because? There is a reason for that, okay? And we will talk about that here in a bit. But there are three questions that I ultimately kind of want to consider, and each of those has a very clear answer. So let's start off with the first one, okay? So the first one is, how do we compute the volume of a given region? And the simplest way of doing that is to just consider the end areas, okay? So the most common method that we will use is to either look at the average end area formula or a pyramid formula. And so average end area would be, if I wanted to compute the volume of this shape right here, what I would do is I would take the average of this area and multiply it by the length. And so I'm going to term that V sub E. So V sub E, the sub E standing for end area, okay? Now, if we have a transition region, what's happening is the shape is not really this sort of prism type shape. It's more like a pyramid, because on those transitions, we're going from an area to a point where the area at the end is 0, okay? And so for those sections, we're not going to use the area of a prism. We're going to use the area of a pyramid. Or sorry, I keep saying area, I should say volume. Instead of using the volume of a prism, we're going to using the volume of a pyramid. And so the volume of a pyramid, we take the area of the base times the length over 3. Okay? And you'll see, like, if it seems a little confusing now, you'll see when we get into our example, it's a lot easier than you would think. So really the only two formulas that we need are the average end area, so take the average of the areas times the length to get the volume, or a pyramid area, or a pyramid volume, where we take the area and multiply it by the length over 3. Okay? Now I am kind of crossing out this prismoidal formula. First off, this box right here comes directly from the FE reference manual, and I'm crossing out that prismoidal formula. I don't really see that used a lot in practice. So it does give you a little bit of a better approximation, because it assumes that you have not just an end area, but an area in the middle. But usually what an engineer or a surveyor would do is just, instead of doing one volume computation, they would just do 2 and just do it separately. So I don't really see that used a whole lot in practice. Okay? That's not to say it isn't used, or maybe some software packages are using it. I just mentioned that for the real world. Okay. Excuse me. So far, so good? Okay. So I want to do an earthwork computation example with you, and I think you're going to find this is really easy. Okay. So I've got here a project, and let me pull this up on the notebook. I've got here a project, and the project is over a distance of how long? From the beginning to the project to the end of the project, how long is this project?
40 feet.
40 feet. From station 20 to station 20 plus 40. That's a distance of 40 feet. Okay? And so I've got areas at all of these different sections. Okay? And so the numbers are kind of wonky, but I'm actually throwing some wonky numbers at you because if you can follow this, you'll follow a simple one a whole lot easier. Okay? And I've got some cut areas and I've got some fill areas, and I want to compute some volumes out of this. Now notice I did throw a conversion factor up here, and I'm saying 1 cubic yard is equal to 27 cubic feet. Because if I have a cubic yard, what is that? It's 3 feet, 3 feet, 3 feet, right? And what is 3 times 3 times 3? 3 times 3 is 9, times 3 is 27, right? So there's 27 cubic feet in a cubic yard, okay? So what we're going to do is we're going to compute some volumes out of this, and I think you're going to find it's really easy, okay? So let's go through the very first one, okay? So what I'm trying to do is I'm trying to figure out the volume between stations, okay? So if I've got station 20 and station 2010 plus 50, I'm trying to figure out the volume between them, okay? So what I'm trying to do is I'm trying to fill in like this box and this one. I'm trying to figure out the cut and the fill volume between them, okay? Whoop. With me so far? Okay. So let's do a simple one. What is the cut volume between these two stations? 0. There is no cut. This is a total fill situation. So this is 0 right here. Okay. Now what about the fill volume? How do we do that? Okay. Well, I think you're going to find it's pretty straightforward. Okay. So here's what you're going to do. Okay. So we have an area here and an area here. So I'm going to take the average of those two. So I'm going to take 173.21 plus 43.56 divided by 2. That's going to give me the average, right? Okay, and I'm going to take that average, and what am I going to multiply it by? What's that? And what is the length? Hold on.
10.5.
Between these two stations. Between these two stations, what's the length?
3.5 units.
Well, okay, we're going to handle that part a little differently. Let's just do it in feet. What's the length here? In feet?
10.5.
10.5 feet. So you're not wrong, but we're going to handle that a little differently. So 10.5 feet. Now, so look at what before I calculate anything, I've got an area in square feet times a length. This is in cubic feet, right? Now, how do I take this and turn it into cubic yards? Divide it by 27. So I'm going to divide this by 27. So see what I'm doing? I'm taking the average of the areas times the length and then dividing by 27. What do I get when I chug this out? 42.15. Do I have a second on that? Okay. So 42.15 cubic yards of fill between these two stations. So far, so good? Okay. If that's the case, what I would like you to do is tell me what goes here. If you figured out this one, then tell me this one. I'm going to let you tell me. And maybe what we'll do is we'll simplify this a bit. This is a length of 10.5 feet. What's the length between these two? 11. What about the next one? 6.95. Do I have a second on that? And then the length here, I think it's what is that? 11.55? Okay. All right. So what goes right here?
10.835.
So we'll say 10.84. Do I have a second on that?
Second.
Okay. All right. Okay. Now what about this one? Do I use the average end area formula? No, because I'm going from an area to 0. This is a pyramid, right? Between these two, right? I'm going from an area to a 0. So what I'm going to do here is I'm going to say, okay, I'm going to take 14.32 over 3 times 11. But am I missing anything?
About 27.
There you go. Okay, so what do we get here? 1.94. Do I have a second?
Second.
Okay. So do y'all see what I'm doing here? So here, what I'm going to have, so in this cell, if I look at, this one right here, you tell me what, actually, you know what? You tell me. Tell me what this value is going to be. You compute it. Is it an end area computation or a pyramid computation? Pyramid, right? Because it's going from a value to 0.
0.83 cubic yards.
0.83. Do I have a second?
Second.
Okay. So 0.83. Okay. So tell me this one right here, and then I'll do the other two. Well, I'll tell you what. I'll do this one because I know this one's easy. That one's 0. You tell me this one.
10.17.
10.17. Do I have a second? Second. Okay. I'll do the last one because I think by now I think you're probably getting the pattern. 53.93. Okay? So, what I'm going to do now is, if you notice the very bottom row, I'm doing a summation. So I'm going to sum everything here and sum everything here. So I'm going to sum all this up. I'll do this one for you because I think you can do this. 66.05. And we'll just indicate, again, that's a cut. And then down here, we get 53.81. That's a fill. So, if this was the end of the story, what would the contractor need to do? Would the contractor need to go find some additional material to bring to the site, or would the contractor need to find a place to truck out all the extra stuff? Is it the first scenario or the second? Second, exactly right. Because we've got this much cut and this much fill. So it's like we're removing this, but we're only placing this. So the difference between the two is how much extra material I have at the end of the day. Make sense? Now, let's go back to, all right, so any questions on this? Okay, now I want to go back to my slides here, because if you remember, I said there were 3 questions to consider. What were the 3 questions? Well, how are the region volumes computed? Well, we figured that out, right? It's pretty easy. How do we handle the unit differences? We figured that out. But this, I didn't talk about that. What is up with this 25%? What is going on there? Okay, let's talk about that. I want to talk about the states of soil and rock in the real world. Okay, so how many of you have ever heard the term in situ? You've ever heard that term before? The term in situ, so if you ever hear the term bank or the term in situ, bank material or in situ material means material in its natural state. Okay, like in place. So that's what in situ means. Okay, loose is what happens after you've taken in situ material and removed it from its natural state. And then compacted is after you've placed it. I mean, this is going to be a silly question, but how many of you have ever dug a hole in your life? Okay, so if you dig a hole that is a box, 1 foot by 1 foot by 1 foot, and then you look at the amount of dirt, it's more than 1 foot by 1 foot by 1 foot. It doesn't seem like it, but it's more, right? There's more dirt there. It's like, where did all this dirt come from? The hole's not that big, right? Well, it's what happens when you take material and you disturb it, okay? So a good example is if you take like solid rock, if you take solid rock and busted it up and turned it into gravel and took that and looked at its total volume, it's going to be bigger than it was in an initial state because there's going to be air voids there, right? Like it's a funny experiment in like you probably have seen something like this in chemistry, or maybe you saw this in middle school. But like, let's say you had like, I don't know, 50 marbles, right? So that were all of an equal size, right? So you can compute the volume of a single marble, right, in milliliters. You can convert it, right? And then you multiply it by 50, and you say, okay, here's the volume of 50 marbles. And then take those 50 marbles and pour them into a graduated cylinder. And look, it's going to be higher than 50 millimeters, right? Because there's all that air between the spheres, right? You can't take 50 spherical marbles and stick them in a perfect container like that, right? This gravel is going to have air voids. It's not going to fit together regularly, right? So to express that in an earthwork standpoint, we have two different terms that we use. We use the term swell, we use the term shrinkage. So shrinkage is what happens when you take a material and you compact it, such that its density is greater than it was during its natural state. And this is very possible for like really fine materials and for clay materials. When you take soil mechanics, you will learn that there are really, there are like 4 different main classifications for soils: gravel, sand, silts, and clays. But really clay is the one that's a little different from the others, because clay has a very, 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 very small net negative electric charge that attracts water, okay? That's what a clay is. A clay is a material that can store water. And so when you compact it, you can disperse some of that water out. So you can take a clay in its natural state and actually compact it and shrink that volume a little bit, okay? So if we're ever dealing with a clay type material, what we might do is we might increase our desired fill volume by some percent to account for the fact that that material can be compacted, right? Whereas the flip side could be something that we call swell. So swell is what happens when we take a material in its natural state and we bust it up and we get a bigger volume than we expected. And so a swell would happen if we're talking about like a rock material. And so if we're talking about a rock material, what we might do is we might increase not the fill volume, but the cut volume, okay? Because when we take that material from its in situ state into a cut state, we get a bigger volume at the end of the day. So swell is when we would increase our cut. Shrinkage is when we would increase our fill, okay? Does that make sense? And so you can look up some common shrink and swell ratios for common materials. So for example, with like rock, it's kind of interesting. Like even if you try and compact the rock, you're still not going to be able to get it back to its in situ state. So even compacted, you're going to have an increased percentage in volume compared to what it was in situ. So for clay, we might up the volume once we make it loose, and we compact it and we decrease it a little bit. So what we'll do from a volume computation standpoint is we'll increase our cut and fill volumes accordingly. Now, the other thing that I'm going to mention to you, and we'll see, I don't want to rush it, but I do want to mention this, is I do want to mention what's called a mass Hall diagram. How many of you are in statics right now and you finally started to assess the ubiquitous shear and moment diagrams? Does that become a topic of discussion yet in statics? It will soon, trust me. So shear and moment diagrams are 2 of the most commonplace tools that engineers use, period. I know the folks who have me for structures right now, they're probably getting tired of them at this point, right? We have used them quite extensively in that class, am I right? So in short, a shear and moment diagram is sort of a representation of the change in forces along a given structure. And in statics, you learn about shear and moment diagrams at a very basic standpoint. But when you get to structures, we do them for real. What I would say is that there is somewhat of an analogy in the earthwork land of things, and we call those mass Hall diagrams. So a mass Hall diagram is sort of like a representation of the change in cut and fills along a project. So if I have, let's say, well, I look over here on top, here's the ground, right? So here's the existing ground, right? And here's the grade line, right? So here's going to be cut, here's going to be filled. Does that make sense? Okay, so the mass haul diagram is just a cumulative effect of all those cut and fills. So like from here to here, right? So we cut and then we fill. So like from here to here, we have an increase in cut, and then when we come this way, that cut starts to decrease. The construction of a mass haul diagram is actually an incredibly simple endeavor. It's much easier than you would think, because all we do is we take our cumulative cuts and fills along the project and we just plot them, and usually we plot them in Excel. We'll probably do that when you come back from break, because I don't want to rush that, and this is an incredibly simple endeavor. If you understand this, then a mass haul diagram is incredibly simple to do. But what I think what we're going to do is when we come back from break, so what we're going to do is we're going to take that previous example and we're going to sort of tweak it a little bit. We're just going to say, okay, let's take that previous example and let's assume that we've got a 25% shrinkage that we need to account for the fact that the material is going to be compacted among once it's filled, and then we're going to plot a mass haul diagram. So we're going to take this example. Numbers look familiar? Notice how we just computed those? And so we're going to take these fill volumes, we're going to adjust them for shrinkage, then we're going to do a cumulative volume, and then we'll plot it. It's incredibly basic, it's incredibly easy, and it's a perfect topic to address after you've had some turkey, right? Because you're coming back and you're like, I don't even remember what we're talking about in this class, Dr. Mike. It's the last week of the semester, we're tired, we just want the semester to be over. Let's just do something easy. Like, okay, we'll do mass haul diagrams because it's really easy. All right, does anybody have any general questions? All right, then I have 2 points to mention. Point 1, do not forget that your topo is due Friday at 1 p.m. And second, I hope you all have a very relaxing and wonderful Thanksgiving break. We will see you when you return.